The advent of digital communications means that information is sent as binary strings over channels that may be noisy. In other words, there may be errors in how the information is transmitted. So occasionally in this string, a 1 will become a 0 or vice versa. And with so much communication these days that relies on digital technology, reading a hard disk, Wi-Fi communication, digital TV, it would be quite bad for us to lose information. How do we ensure that information does not get corrupted due to noise? One way you might solve this problem is to just repeat information. So, if you're trying to send 4 bits of information, like the string 1101, you could send the 8-bit string 11011101 and hope that the string never accumulates more than one error. If so, you could tell when a string was corrupted. It might look something like 11011001. In this case, you see that the second bit of the 4-bit string was corrupted. So you could detect an error. But you would have no idea how to correct the error. Was the second bit a 1 or a 0 to begin with? A binary string like 11011101 is called a code vector. Code vectors are how you represent some information. And the set of all code vectors is called a binary code. The method of duplication we just discussed for encoding information will allow us to detect when an error has occurred. And for that reason, it is called an error detecting code. However, it does not tell us how to fix that code. If it did, it would be an error correcting code. One way to make an error correcting code would be to triple the information. So to send 1101, you might use the code vector 1101, 1101, 1101. Then, if a single bit got corrupted, you could infer what the original was by noting which 4-bit string appears twice. However, tripling the information could be costly in terms of the bandwidth needed to deliver such information. A more efficient code is something called a Hamming code, and it involves looking at the following Venn diagram. The idea is to take a 4-bit string like 1101 and replace it with a 7-bit binary code vector by adding 3 check digits to it. These check digits operate in such a way that if any one of the bits in the 7-bit string gets corrupted, you can figure out which bit it was and fix it. The way to produce these check digits is to put the bits 1101 in positions 1, 2, 3, and 4 in the picture. Then we compute check digit in position 5 by setting it to be 0 or 1, so that the number of ones in the circle around 5 is even. We do the same for positions 6 and 7 similarly. This code is error correcting because if there is a single error in this 7-bit string, you could determine which bit it was by looking at the 3 check digits. Depending on which check digits look wrong, you will know which cell in the Venn diagram was an error. For instance, if check digits in position 5 and 6 are both wrong, but position 7 is correct, you will know that the digit in position 2 is the one in error. Or, if you look at the check digits in positions 5, 6, and 7, and they're wrong, you would know the digit in position 4 is in error. And if only the check digit in position 6 is wrong, you would know the original 4-bit string is correct, and it was only the check digit that got corrupted. You see, this is a clever and efficient error-correcting code. The Venn diagram is a handy way to think about the code, but it doesn't reveal the fact that there is some linear algebra behind how you would design such a code, as we shall soon see. Now, in the last couple of lectures, we've dwelled on vector spaces and the algebra of vectors. We've seen how to take linear combinations of vectors to produce lines and planes and other linear objects. We saw that as ordered collections of numbers, vectors in Rn can be written as a row vector or column vectors. In this lecture, we want to introduce a new object, a matrix, which is an array of numbers. By the way, I should say, since you'll use this word a lot, the plural of the word matrix is matrices. An m by n matrix is an array of numbers with m rows and n columns. We write A equals, parentheses, A sub ij, close parentheses, to tell the reader that A sub ij is the entry in row I in column j. For example, if A is the 2 by 3 matrix with entries 1, 2, 3, 4, 5, 6, then A sub 2, 1 equals 4. To say that two matrices are equal means they have the same dimensions and their entries are identical. We might notate that by writing A sub ij equals B sub ij for all I and j. To add two matrices, we add their corresponding entries. For example, look at these matrices, D, E, and D plus E. Here you see, for instance, in the bottom right corner, that 4 plus 1 equals 5. Now, to multiply a matrix by a scalar, we multiply every entry in the matrix by that scalar. So if we take the matrix D as before, with entries 1, 2, 3, and 4, the matrix 1/2 D will be 1/2, 1, 3/2, and 2. Now, there is a notion of a product of matrices, but it'll seem strange at first, so let me first try to motivate it. Suppose you have some variables, y1 and y2, written as linear combinations of three variables, x1, x2, and x3, as in this example. Suppose also that you have the x variables written as linear combinations of the variables w1 and w2. By simply substituting the second set of equations into the first, we can obtain expressions for the y variables as linear combinations of the w variables, like so. Now suppose we write matrices that represent coefficients in these changes of variables. There's a relationship between the entries of the matrices, and let's see what it is. First of all, the dimension of the y in terms of x matrix is 2 by 3. Since there are two y variables and three x variables. The dimension of the x in terms of w matrix is 3 by 2, since there are three x variables and two w variables. So the dimension of the y in terms of w matrix is 2 by 2, reflecting that there are two y variables and two w variables. Secondly, the fact that there is a 15 in the bottom left corner of the 2 by 2 matrix refers to the number of times w1 appears in y2. And if you look at where this comes from, it comes from multiplying the number of times a particular x variable appears in y2 by the number of times w1 appears in that particular x variable, summed over all x variables. If you look closely, you see this computation is just the dot product of the second row of the first matrix with the first column of the second matrix. The pattern in these changes of variables suggests a natural notion of multiplication of matrices, which we now define carefully. First of all, if you want to multiply two matrices A and B, there have to be conditions on the dimensions. The number of columns of A must be the number of rows of B. Then you can form the product A times B, which we will call C. Then if A is an M by P matrix and B is a P by N matrix, the matrix C will be M by N. To get the ijth entry of C, Take the dot product of the ith row of A with the jth column of B. This is called the row-column formula. Note that the order of multiplication matters greatly. Even if A times B is defined, the product B times A may not be. And when they are both defined, it is not true in general that A times B equals B times A. So matrix multiplication is not commutative. You should stop this video now and find some matrices for which A times B and B times A are both defined, but their products are different. Now, examine this product again, and let's check the other entries. Take a moment to verify that the entry 4 in the first row and second column of C is the dot product of the first row of A with the second column of B. Since the second column of B is a standard basis vector 0, 0, 1, notice something interesting, that the dot product just picks off the last coordinate of the row 3, 1, 4, which is a 4. In fact, a similar thing happens with the second row and second column of C. The column 0, 0, 1 picks off the last coordinate of 1, 5, 6, which is a 6. The final entry at the top left is the dot product of the row 3, 1, 4 with -1, 2, 1, and it is indeed 3. Aside from representing compositions of linear functions, matrix multiplication can be used to express a system of linear equations in a nice way. We'll say more about what a linear equation is later, but for now, just think of them as a linear combination of the variables that are set equal to a constant. So for instance, this system of equations on the left is a system of linear equations, because both equations are linear combinations of variables set equal to constants. The system of equations on the left can be expressed as a matrix equation on the right, where you have a matrix times the vector x1, x2, x3 equaling the vector 1, 5. Notice that a column vector x1, x2, x3 is just a 3 by 1 matrix, so the usual rules for matrix multiplication applies. What's great about a matrix equation is that you can express a large system of linear equations like this, in this very compact form. Here, x and b are column vectors. And it can be helpful to have this point of view. The matrix A is acting on the vector x to produce the vector b. Let's look at another example where matrix multiplication is natural. Suppose you're trying to get from one city to another through a hub like Dallas, Chicago, or Denver. To make things simple, suppose the first flight is in the morning and the second flight is in the afternoon. You want to know the number of possible flight paths that will get you from the origin to the destination. If you had a matrix counting flights between origin cities and hubs, and another matrix counting flights between hubs and destinations, then a nifty fact is that the matrix product naturally counts the number of ways to get from any origin city to any destination city. For example, suppose you wanted to get from Ontario Airport near Los Angeles to the Boston Airport. If there are 2 flights from Ontario to Dallas in the morning and 4 flights from Dallas to Boston in the afternoon, then there are 8 total ways to get from Ontario to Boston through Dallas. Similarly, if you knew the number of flights from Ontario to the other hubs, and from these other hubs to Boston, you can see that the dot product of the Ontario row with the Boston column will give you the total number of ways to make that trip through various hubs. Here the dot product of 2, 3, 0 with 4, 3, 7 is 17. What you may notice after doing several examples of multiplication is the following fact. that if the columns of B are called B sub I, then the columns of the product A times B are just the column vectors you get by doing A times B sub I in the corresponding columns. Moreover, if you take a matrix A and multiply it by the jth standard basis vector E sub j, then you just get the jth column of A. Take a moment to think about why this is true. For each row of A, the 1 in the jth position of E sub j just picks off a single entry in the jth column of A. This means if you fill a matrix with the standard basis vectors in order, you get a matrix that, when you take another matrix and multiply it on the right by this one, it stays unchanged. Like this example. We call this matrix here the identity matrix. It is always a square matrix with 1s along the diagonal and 0s everywhere else. We often use the letter I to denote it, or sometimes I sub n if we want to remind the reader its dimension. Similarly, if you want to pick off rows of the matrix A, you can multiply it on the left by the row vector E sub I transpose. That will produce the ith row of the matrix A. So, matrix multiplication by the identity matrix on the left will leave its rows unchanged. So to summarize, if you take an m by n matrix A, you can multiply it on the left by I sub m, or on the right by I sub n, and it will stay unchanged. This identity matrix is what's called a multiplicative identity. We point out that there is also an additive identity, that you can add to any matrix and leave it unchanged. It is just the zero matrix, the matrix of all zeros. Every matrix also has what's called an additive inverse. That is, a matrix you can add to it to get the zero matrix. Clearly, the additive inverse of A just puts a negative sign on every entry of A, and we'll call it a special name, minus A. There are other properties of multiplication we should mention. First, we highlight again that multiplication is not commutative. Generally speaking, the order of multiplication matters. You should try a few examples to convince yourself this is true. Here's one example. So whenever I write a matrix product, I must pay attention to the order of multiplication so that I don't accidentally switch things around. A very important property of matrix multiplication is the way that it distributes over addition. Thus, A times B plus C is AB plus AC. This is called the distributive property. This can be shown by writing out the expression for the ijth entry of both sides using the row-column formula. If you do this, like so, you'll see that the distributive property follows from the distributive property of the real numbers. You might pause the video here to see if you can see how I've computed the ijth entry of the product of A with B plus C. Even though matrix multiplication is not commutative, it does have an associative property, which may be surprising because it is not obvious at first glance. The proof is a little bit involved if you try to write out the entries on the left and right using the row-column formula. I'll show you how to do it here, but do not worry so much about following the argument if you find the symbols confusing. Later, you will see how it makes sense intuitively when we talk about linear transformations. If we look at the product A times the product B times C and write out the expression for the ijth entry, you will get a sum over some index, call it K. Now write out the expression for the kjth entry of BC. You will get another sum over an index L. If you manipulate this by switching the order of the sums, you can see it will give the expression for the product first multiplying A times B and then multiplying by C using the row-column formula. There's a natural operation on a matrix that switches its rows and columns. called the transpose. To denote the transpose of A, we write A with a superscript T, and if the entries of A are little a sub ij, then the entries of A transpose are little a sub ji. As an example, the matrix with rows 1, 2, 3, 4, 5, 6 has as its transpose a matrix whose columns are 1, 2, 3, 4, 5, 6. A matrix that stays unchanged when performing the transposed must be a square and have a symmetry about the diagonal that goes down and to the right. We call such a matrix symmetric. Here are some properties of the transpose. The transpose of A is just itself. The transpose of a sum is the sum of the transposes. The transpose of a scalar multiple of A is just the scalar multiple of the transpose of A. Less obvious is how to take the transpose of a product. If you examine the dimensions of AB, you'll see that for the transpose, you have to reverse the order of the product for the dimensions to work out right. So the transpose of a product AB is B transpose times A transpose. To prove this is not hard. You just have to check that the jth entry of AB is the ijth entry of B transpose A transpose using the row-column formula. But the left side is just the dot product of the jth row of A with the ith column of B, and the right side is the dot product of the ith row of B transpose with the jth column of A transpose. But these are just the same quantity. Now let's return to the error-correcting code we discussed earlier. How do we create an efficient binary code like the one we demonstrated with the Venn diagram? Is there an easy way to determine the check digits without having to look at this diagram? What we want is a way to transform a 4-bit message vector to a 7-bit vector. Given how toggling one element of the 4-bit vector changes check digits in precisely the same way, no matter what the starting state is, we have good reason to believe the transformation acts linearly. So let's see if it can be represented by a 7x4 matrix, called the generator matrix for the code. The first thing to note is that we will be working over a binary field with just 2 elements. This means we're only going to use the numbers 0 and 1. Think of them as symbols. And we have addition and multiplication defined just as you would expect if 0 signified even and 1 signified odd. Since odd times odd is odd, we'll have 1 times 1 equals 1. Since odd plus odd is even, we'll have 1 plus 1 equaling 0. Our matrices and our scalars will use elements from this binary field with just 2 symbols, 0 and 1, rather than using real numbers. Then the generator matrix G should look like this. Notice, the highlighted part of this matrix is the identity matrix, and it takes the 4 bits of the message vector and just puts them without change in the first 4 positions of the 7-bit output vector. So, if my message vector is, say, 1, 1, 0, 1, then when I multiply G by the column vector 1, 1, 0, 1, you will get a 7-bit vector. The first 4 terms of this vector, which come from the highlighted rows times 1, 1, 0, 1, will give 1, 1, 0, 1. The other part of the matrix computes the check digit. So for instance, the 5th row adds the numbers in positions 1, 2, and 4, and that gives the check digit for the position 5. For instance, with the message vector 1, 1, 0, 1, the 5th row times 1, 1, 0, 1 is 1 plus 1 plus 1, which is 1 in the binary field. And this is exactly what the Venn diagram suggests. You can see in general that the check digit will produce whatever is required to keep the number of ones even in the Venn diagram, that circle that's around 5. Similar statements hold for rows 6 and 7 and positions 6 and 7. So if you multiply G by the message vector as a column vector, 1, 1, 0, 1, you will get the column vector 1, 1, 0, 1, 1, 0, 0. Now there's also another matrix called the parity check matrix, P, which should take a received code word and check if it is a legitimate code vector. So it should take in a 7-bit vector and spit out a 3-bit vector, 1 for each check digit. It is a 3 by 7 matrix that looks like this. Here you can see, for instance, the dot product of the first row with a code word will add positions 1, 2, 4, and 5. So it is performing the parity check for the circle surrounding position 5. Since similar arguments will hold for the other 2 rows, you can see that the blue part of P must be the same as this part of G in order to perform the parity check. Since we expect genuine code vectors have check digits all 0, then since for any vector v, G times v is a genuine code vector, the matrix product P times G times v must be the 0 vector, which suggests that P times G times any v will be the 0 vector. You can check that indeed the matrix product P times G equals the 3 by 3 0 matrix. Let's see what it does with the code word we generated earlier, 11011100. If you multiply P times this column vector, you will get the column vector 0, 0, 0, which shows it is a valid code word. And indeed, it came from the message vector 1101, as we saw earlier. Now let's see what happens if a received code word has a single error in it. Then it will be a genuine code vector, v, plus some e sub I, a standard basis vector. That e sub I signifies the error that was introduced. When you apply P to it using matrix properties, we see P times v plus e sub I equals P times v plus P times e sub I. And since P times v equals the 0 vector for a genuine code vector, and P times e sub I is the ith column of P, the output is just P times e sub I. So we know which location is faulty because the output vector will mimic one of the columns of P. So the output will reveal the location of the faulty position I, as long as all the columns of P are distinct and never the 0 vector. If P times e sub I is the 0 vector, the parity check will be the 0 vector and not reveal an error. So let's try this on the code word we generated earlier, 11011100, and suppose it is corrupted with a single error, so that it is now this code word, 11011110. If you multiply P times the column vector, 11011110, you will get the column vector 0, 1, 0. The fact that this is not the 0 vector means there was an error. And now we just check which of the 7 columns of P is 0, 1, 0. And we see it's the 6th column. So the problem is with the 6th entry of the code word. Pretty neat, right? Let's try this again with 11011100 and now corrupt the 3rd entry. So it is now the corrupted code word 11111100. If you multiply P times this as a column vector, you will get the column vector 0, 1, 1. This, if you check, is just the third column of P. So it must be the third entry of 1111100. That is incorrect. And indeed it is. The particular code we chose was extremely efficient because P contained as many distinct columns as possible. You can't have more than 7 distinct non-zero binary vectors of length 3. This code actually has a special name for that reason. It's called the 7,4 Hamming code. Our analysis also shows us how to generalize this construction to longer initial messages. If you want to have a matrix P with all possible non-zero strings of length 4 instead of length 3, you will need 15 columns. So n should be 15. But then the original message length should be 11. This leads to the construction of another code called the 15,11 Hamming code. So in this lecture, we've defined matrices and their algebra and seen several applications of the idea of matrix multiplication. As it turns out, matrix multiplication is intimately tied with the idea of a linear transformation, which we will explore next time.